And why not gradient boosting trees? Why? Because they are pretty fast to train, doesn't require too fancy feature engineer. They have very good results, and they are interpretable. Uh, Before explaining a decision tree, I want to ask you who have worked or are working or at least have the basic knowledge about what means a decision tree, random forest. That's cool. Because it's a plus to have this basic knowledge to better understand what I'm gonna explain in the presentation. So this is how a decision tree looks. You can see that here we have a very simple one with the depth equal to 3. You have only few nodes. In matter of minutes, you can understand what the nodes means. And yes, you can say that this tree is interpretable by us, by a human. But let's look what happens if you increase the depth of the tree. You can see that now the tree is way more complex, contains a lot of information. So this is the case when you have a big data set or a complex data set where we are forced somehow to increase the depth of the tree to have better performance of decision tree random forest. And if you are familiar with sklearn library, with Python, you know that this is the most used visualization for a decision tree in, let's say, in a Python sklearn community. And this, like you see, it's pretty hard to understand what's behind this structure. Yes, and that's why I started to work on a library from scratch to help me to better understand what's happening behind the machine learning model. And when I started to develop this library, I started with two main ideas into my mind. First is to help me to better understand the model structure and the model performance. And the second idea was to explain the model prediction. And this is how the woodpecker appears. So it's in its first version, it's version 0.2. And right now it contains implementation only for decision tree classifier from sklearn. But really soon I'm going to implement decision tree regression and random forest. And why not, based on your feedback, your suggestions, I can add more functionalities and new features. If you want, you can take a picture to scan the QR code or to go to the Git link and to see and to try it. So now let's switch to the Jupyter notebook and see what the library can do and to see if for you it could be helpful. So I'm going to start from here. I just prepared the data set. Like any machine learning model, right, we need a data set to work on. In this case, I choose the Titanic dataset. It's a very well-known dataset. It's a small but interesting. Can I make? It's okay. I guess. Yes. And this dataset contains each row from the dataset is a passenger from the Titanic. And we have many characteristics for each passenger. For example, we have the P class, which represent the social economic status. 1 mean upper social economic status, 3 mean lower. We have the age, which is the passenger age. We have the fare, which is the how much money the passenger paid for the ticket. We have the sex label, which 0 means female, 1 means male, and so on. You can read yourself. And our target as a machine learning engineer is to predict the chance to survive. 0 means didn't survive, unfortunately, and 1 means the passenger survived. So here it's a simple sample from the dataset to see how it looks for machine learning. Yes. With this dataset, we need to split it into the training and validation. This is how. And with few lines of code, you can already train a decision tree classifier on the training set. And now let's imagine that we just received the data set, we have a little knowledge about the data set, and the first intuition is to set the depth of the tree to 10, because it's let's say it's a common value for the depth of the tree. And here I'm showing you the accuracy on the training set, on the validation set. And you can see that for training, accuracy is pretty good one, 0.91, but for validation is 0.82. Do you know what's happening behind? Why do you have a lower accuracy on the validation than the training set? Okay. Sorry? Yes, which is mine. Yes, we are overfitting. And this is happening when our decision tree classifier learn very well the training set and didn't make good prediction on the validation set. But if you look at this picture, like I said, a lot of information here, we don't know for sure why our model is overfitting. And like I said, this is the official visualization for decision tree from sklearn community. But let's see how we can interpret this tree using the library. So in the library, I created the class decision tree structure, and I'm initiated it with the parameter decision tree, which I just trained, the training set, the feature, and the target. Let's create it. And in the next visualization, I'm going to show you the first goal, understand the model structure and the model performance. Yes. But before showing the first visualization, I just want to tell you about the node structure. In a decision tree, we have two types of nodes. You have split nodes and leaf nodes. The split nodes are used to split the data set, or more specifically, to split the feature spaces. And the leaf nodes are those ones that are used to make the final prediction. And when you hear the final prediction, you can guess that these nodes, the leaf nodes, are the more important one from a decision tree. And that's why it's important to have a general overview about what they are doing. A leaf node contains two types, so at least two important information. This is the impurity of the leaf samples. The impurity for a leaf node shows how much the leaf is confident about its prediction. So it's a value between 0 and 1. If the impurity is 0, that means that the leaf is very confident about the prediction. And the opposite is if it's 1, the leaf it's 50-50 chance to make a good prediction. And also the leaf samples metric shows how many samples from the training set arrive in that leaf. And these two information are very important. And in the next visualization, we are gonna show them. So you can see, I have here a simple method that returns the number of leaves from the tree. And here in this visualization that I created with the library, it shows us a general overview about the impurity in the whole tree. As you can see, majority. So on OX we have the impurity value, and on OY we have the number of leaves. And you can see that majority of the leaves have impurity 0, which is somehow an ideal case to have majority of leaves to have very good prediction. But why do we have still our decision tree is overfitting? Let's look at another visualization which shows the number of samples from the leaves, and you can see clear that also the majority of the leaves contains very few samples. And this is a clear sign of overfitting because we have in our leaf, we have very, very few samples that reach that leaves. So yes, the model learned the training set very, very good, but on the validation, it has bad performance. And yes, using these two visualization, it's a clear sign of overfitting, and we know why. And from here, with this information, what we can do, for example, we can decrease the value of the depth of the tree, and you can see what's happening then. Yes. In above two visualization, we saw a general, let's say, overview about the impurity and the number of samples from the list. But what if you want to see this information on each leaf individually? So I created these two visualizations. In the first one, on the OX represent the node ID, and OY represent the impurity value. So from here it's clear that majority of leaves have impurity zero, like we saw in the above visualization. But this one is really interesting one. We can see here on OX we have again the leaf node ID, and on OY we have the number of samples. And by color by blue color I represent the class 0, and the orange color I represent the class 1, which means survive. So if you look at these leaves, you can see that something interesting. You can see that this leaf contains a lot of samples from the training set, or for example, these leaves contain only samples from the training set which survive. So why? If it's interesting to ask why the passenger from this leaf with number 25 survive in the Titanic. So it was interesting for me to find out why. So I created a method to get me the samples from the training set which arrive in this leaf. So I can call the get node samples with node ID 25. With 25 is this one. I don't know if you see, but this is the leaf node ID. And we can look at all the samples from the training set arriving in this leaf. It's a pretty big one. It contains 62 rows, but to have let's say, a general overview about this information, we can call the describe method from the pandas data frame. So let's look at these statistics. I'm better. You can see this. The count is 63. We know that for P class, the mean, so the average is almost 1, and the standard deviation is pretty close to 0. That means that almost all the passengers from this leaf are from P class 1, and P class 1 means that they have a good social economic status, so they are kind of rich. If you look at for example, at the age, the mean is 30. Standard deviation is a little spread, so it means that the passenger, I don't know, let's say are between, most of them are between 20 and 40. So you know that this passenger are, let's say, young to mid-age people. Let's look at the sex level. The mean is 0, and the standard deviation is also 0. That means that all the passengers are female. And definitely they all survive. So looking at this information, we know that if you are a woman, a rich woman, young and to mid age, you had a very good chance to survive on Titanic. That's interesting. We know why, because the woman and children have the priority when boat crash is happening. But if, like I said in the beginning, let's say we don't know too much domain knowledge about this data set, and this is the way we can find it. And this is the way you can find patterns in data and get more domain knowledge about the data set. And I do believe that getting domain knowledge about the data set, it's a very important skill for a machine learning engineer, because if you have the domain knowledge and try to apply it into, let's say, machine learning, that's the ideal case. Yes, sorry. Yes, here it is. So let's say we can look at another leaf, for example, this one, which is the opposite of the leaf I just presented. All the passengers from these leaves didn't survive. And can you tell me, before showing you the describe method, which kind of person are in this leaf? The man? Yes, maybe. Let's see the leaf number is 98. Yes. So this is the list, and let's go to the describe method. So yes, you are right. You can see that the mean is almost 3. Standard deviation, it's very low, so it means that all the passengers from that blue leaf are from P class 3. And P class 3, if you remember, represent a lower social economic status. So lower social economic status means they are poor, yes. It's interesting to look at the age. It's 16, and a low standard deviation, pretty low standard deviation. So they are kind of young people. The fare, it means how much money they paid for the ticket, is 10. So it's pretty low from the average. The average is somewhere 30, if I remember correctly. So they are lower than the average people pay for the ticket. And yes, and the sex label is 1, which means that they are male. So in this case, we saw another pattern in the data. Like you said, like you guess, they are men, young men, and poor. They had a very low chance to survive. And again, this is how, if you are working on a machine learning project at work, this is how you can get domain knowledge about the data. Yes, and the second idea I started to create a library is to help me to explain or justify the model prediction for a technical or non-technical people, especially for decision tree. It happens to me to be asked why your model has this prediction, like 0.2, 0.9, and so on. And my answers were because it's machine learning model, it's a decision tree behind, it's a mathematical, let's say, algorithm behind. Or another option was to take that big picture and to try to follow the prediction path on that big decision tree. And that was a problem because, like you remember, there are a lot of nodes and it's pretty tough to track the prediction path. And that's why, sorry. First, let's take a sample from the validation, or random sample. And you can see that the P class is 3, the age is 45, and so on. And in this case, if someone will ask me again why your model, decision tree in this case, has that prediction, I can very simply explain why. I can look at all the prediction path from the tree. And as you can see, instead of showing all the tree, now I visualize only the prediction path with the blue bullet. Yes. So you can see that in this case, the sex label in our case is 0 and is lower than 0.5. it goes to the left. If the P class, which in our sample, if you remember P class, where is P class? Here is 3, is bigger than 20.5, and it goes into the right, and so on until the leaf node. And this leaf will make the final prediction. You can see that we have 11 samples with class 0 and 0 sample with class 1. So impurity is 0. So this leaf is pretty confident that that's the sample didn't have the chance to survive. Yes, I guess that's all. Thank you for staying to my presentation. I know that I guess it's the lunch time. I would really like to ask your question, and why not to offer me suggestion how to continue to improve this library, and why not maybe you are gonna try to use it. Thank you.
Thank you. Awesome. Thank you so much. Any questions? I know we are between you and lunch, so.
You are not hungry, right?
Cool. So have a good lunch. And we'll see you back in about 45 minutes or an hour. Yeah, about an hour. We're going to start our afternoon sessions. Thank you so much.